And today I'm just going to be talking about the basics of the forensics category. So what is in the forensics category? In here, you'll pretty much see any type of problem that has to do with finding flags inside of files, memory dumps, images, and more. It can also involve zip cracking, file carving, steganography, and a bunch of other things. I'm going to go over most of these in this talk today. And yeah, it's honestly, forensics is kind of like fuzzily defined, and sometimes you'll see forensics problems put in the miscellaneous category rather than on their own, just because they're kind of hard to categorize. But so the first thing I want to talk about is files. So what really are files? So if you break it all down at the very basic bits of files are ones and zeros, right? You know, a file, like however you view it on your computer, is just a nice representation that you can look at of ones and zeros. So, you know, computers will make it look all nice that humans can understand it, because like looking at a bunch of ones and zeros isn't very useful to us. But yeah, at the very lowest level, it's just a computer interpreting bits. So how are files stored? All these bits get added together into a giant binary string. So there's like thousands, millions, or trillions of ones and zeros in a row, which represent the file's data. And so a bit can only have two options, 1 or 0, which is like equivalent to on or off. And, you know, this giant bit string representing a file is a lot to work with. So we break it down into something more manageable, which are bytes. So a byte is 8 bits, and it can be represented by a decimal, which is like base 10 number. So starting at the right and moving left, each position represents a power of 2. Can y'all see my mouse?
Yeah.
Okay. So a 1 or a 0 will tell us at these different like power positions if we want to add that power of 2 to our number. So here on the right, this is like the lowest value bit, 2 to the 0, which is equal to 1. And we have a 0 above it, which means we're not going to add that to our like sum. So down here we have a plus 0. And the same thing for 2 to the 1, which is equal to 2. For 2 to the second power, which is equal to 4, we have a 1 in that position. So we do want to add this. So we add, you know, plus 4 to our sum. And if we do this for all 8 bits in the byte, you can see we did it for just 3 numbers here where there's a 1 in that position. You add these all together and you get 44. And that's how you calculate, like from a binary number, you calculate the decimal value. And then it's kind of similar to go backwards. You just like keep dividing by 2 and then mark like whether or not there's remainders. I forget the exact thing, but yeah. So if we do a little math, we can see that each byte has 2 to the 8 minus 1 possible values. So like these 8 bits is how many values it can hold. And this doesn't really help us too much. It's still a long like string of data to process, even if we were to represent it as like binary number or decimal numbers. So how can we shorten that? That's where hex comes in. So hex is base 16. So it's the numbers 0 through 9 and the letters A through F. And they represent the values 0 through 15. And you can usually tell if something is written in hex because it'll be prefixed by 0x. And since 16 is 2 to the 4, we can only represent 4 bits of data with 1 hex character. So in order to represent a byte, we need 2 hex characters. Yeah, so you can see here we took the same number from the last slide. We split it in half. So we have the lower half over here. We just calculate this the same way. We have the 8 and the 4 for the 2 positions where there's a 1, and then the rest is all 0. So you add these together to get 12 in decimal, which you convert to in hex is 0xc. And on the left higher value bit side, we just have, we have this, you basically like start over again instead of having, you know, 2 to the 4, 5, 6, and 7 over here. You basically start over and do 2 to the 0, 2 to the 1, and 2 to the 2, 2 to the 3. We calculate this based on like where the 1s are, and then we get 2 in decimal, which is also 2 in hex. And so you just kind of like concatenate these together to get 2c in hex. So most of the time you'll see files represented in hexadecimal, since it's way more compact than binary, and it's also easier to think about than base 32 or base 64. So file extensions. So like I said earlier, files aren't really a thing to computers. It's just like a big chunk of bytes. So files exist to help humans understand what's going on, and that's pretty much it. So like file extensions, I mean. So file extensions like .txt or .jpeg, they're mainly there for the humans. All of the information about what type of file it is stored inside the data of the file. So like your computer isn't looking at, you know, the file extension to figure out what type of file it is. It may use that to figure out what program to open it in, but it actually can tell what type of file it is by some, we'll talk about this later, but some data at the beginning or the end of the file. So anyways, point is, if you change the file extension of a file, just like in the File Explorer or something, you may confuse a human and, you know, maybe it'll open in the wrong program on your computer, but you haven't changed what type of file it is for the most part. There's, I think, some operating systems or File Explorers where you can do that and then it'll go and change the actual file type. But for example, if I just like rename foo.txt to foo.png, the contents inside are still a text file, and you can go open this quote unquote image in a text editor and see the exact same contents. The contents haven't changed. Like this, us changing the extension of the file effectively like didn't do anything to the actual file. So people do this a lot in CTFs. So they might just like, you know, change a file extension to try to throw you off a little bit or like make it open in the wrong program and make you think it's broken. So whenever you get a file in a CTF, run this is a Linux command in your terminal, file on it. And so basically what this does, so here we have this file foo, and like also if they remove a file extension, you don't know what type of file it is. So we have this file foo. If you run the command file on it, it'll give you all this data. It'll look at, again, I'll talk about this later, but look at like the first few bytes or at the beginning or the end of the file and determine what type of file it actually is. So for example, in this case, foo was a JPEG. And besides telling you what type of file it is, it'll also give you, like for JPEGs and PNGs, it'll give you some extra information so you can have like the resolution, density, all this other stuff. Yeah. So how do the computers actually know what type of file it is without looking at the file extension? So there are these things called magic headers, and they're also known as magic bytes, file signatures, file headers, any combination of those two words. But essentially what it is that like for every specific like file format, there are a set of bytes, a unique set of bytes that have to be either, well, they have to be in a specific position in the file. So for example, in JPEGs, they have these 4 bytes, which are put always at the beginning of the file. So if you were to open like a JPEG image in a hex editor, or if you ran like hex dump on it or something, you will see that the first 4 bytes you see are FFD8, FFDB. And so for other file types, I think zip puts like its file headers at the bottom, which is another thing. Yeah, so this is what I was talking about. Zips have theirs at the bottom and JPEGs have theirs at the top. So you can concatenate a JPEG and a zip file together to like confuse your computer, because I think it'll render it as a JPEG because it'll start like looking from the top, or it'll show you that it's a JPEG. Yeah, so you can like mash those 2 files together and you've essentially like hidden the zip in the image, and the image is still viewable. It looks normal unless you were to like open it in a hex editor. And it also works for things which are like derivatives of zips or like still use the zip format. It works for, I forget what it is, like jar files. Jar files are like based on the zip format, so you can concatenate like an image and a jar file and stuff like that. So in terms of CTFs, you'll usually get problems like if you try to open an image or something or a file and it gives you an error. One of the common things that like the problem writers will have done are they will either have like deleted the file headers, so like replaced them with zeros, or just like actually deleted those 4 bytes or however many bytes it is, or they'll have like an incorrect header, so they'll have changed it to garbage or something else. So how you can fix this and how you solve these problems is you can use a program called a hex editor. So basically it does exactly what it sounds like. It'll open like the hex representation of the file, and then you can go and like edit the hex and delete and insert and whatever you need to do. So the one that I like to use is called Bless. It's for sure on Linux. it's on like Chrome OS that Chromebooks use. I think it's on Windows and Mac. But it's free, it's easy to use, and you can just open the file in it, delete the first like few bytes that you need to replace or change, and then save it, and then you're done. And so this list linked here, I won't open it right now, but Wikipedia basically has like a giant table. It's a huge list that has all of the like, honestly, not even common, like common and obscure file formats and their magic header bytes. So like if you get a file that should be a JPEG, but you go and see that, you know, the first 4 bytes are missing, but you don't know what to replace it with, this Wikipedia page is super useful. I go there all the time to like go and find what bytes I need to fix. Another common thing that you'll see is hiding the flag, like the text flag, in the metadata of the file or somewhere within the file itself. So for example, one of the problems I just did on this most recent CTF was putting the flag in like the comment field of a JPEG. And since you can like, you know, put the file in different metadata fields, or you can hide it all sorts of ways, the easiest way to solve this is to use, again, a command line program called strings. And it does exactly what it says on the tin. It goes through whatever file you hand it, and it prints out anything that looks like a string. So anything with printable characters. Now, sometimes this will like print out garbage because it's like, oh, these bytes just happen to also be ASCII values, so they print out. So if you, well, you should know what the format of the flag you're looking for is. And so what you can do is you can run strings on, for example, this file foo that we got, and then pipe it, which basically just like passes the output from strings to be the input of this next program, which is called grep. So basically it says like, take the output of strings and use it as the input to grep. And what grep does, it basically just like searches through whatever input you give it for this like search term you give it. So basically what this whole command is saying is run strings on foo, so print out like every printable string in the file foo, and then pass all of those strings onto grep, who will then search for UT flag. So, you know, besides running file, like the immediately next thing I would try is running strings on it and grepping for UT flag or whatever the flag format of the event that you're in is. So these are just like quick things that you can try just to try to get like low-hanging fruit. So this can also be used on non-forensics problems. So some like easy reversing problems, they'll just like have the flag hard-coded. And sometimes they don't even mean to do this. They just like accidentally hard-coded the flag or something, and you can run strings and like solve it way more easily than it was meant to be solved. Next thing I want to talk about is file carving. So I kind of was talking about this earlier with like the squishing the JPEG and the zip together. So another problem you'll see is that problem writers will hide files within files, or they will concatenate multiple files together. Basically, they'll just like mash up files. So there is a Linux tool, which is really cool. You need to install it. It's not automatically installed. It's called binwalk, and it'll basically just go through a file and look for those file headers that I was talking about, and then print out what kind of files it sees within this like one file that you passed it. So if we ran it on this thing called foo, you can see that it has a JPEG, but it also has like this zip archive embedded in it. So, you know, usually JPEGs are not zip archives. So you can see, oh, maybe I should like look into this zip archive. So to extract these files, there are these two tools, Scalpel and Foremost, which will help you like carve out the files from within the file that it's hidden in. Another common problem is zip cracking. So where you're given a zip archive that's password protected, and basically you just have to like get into it. So most of the time, the password is one from like a top blank most common password list. So it'll be like a password from the top 10,000 most common passwords. So you can use tools like fcrackzip, John the Ripper, or Hashcat to automate figuring out the passwords. So this command here is you're running fcrackzip, and you're running it with a dictionary, and I forget, like this is like verbose, I forget what U does. Oh, U is try it with unzip, the command unzip, to see if the passwords work. And basically, so you're passing it, giving it this password list, which just is like it sounds, it's a list of a bunch of passwords that it's going to try. And then you're trying it on the secret.zip file. So it'll basically run and it'll find the password. So in this case, it was QWERTY123. So you can get good password lists from GitHub or RockU, which is like the de facto password list. It's like a few gigabytes, which if you think about how much text file, how big text files usually are, like that's huge. It has a ton of passwords in it. And then the last thing that's pretty common for forensics is called steganography. So, you know, cryptography is like hiding information, but steganography is hiding information and you're hiding the fact that you hid information. So if someone were to get a file that has some data like steganographically hidden in it, they shouldn't be able to tell that something's up with the file, or like they shouldn't be able to tell that, you know, you've hidden something in there. Because, you know, if you look at crypto, you see like all these jumbled numbers and jumbled strings, like obviously something's hidden in there. So for CTFs, this usually means hiding information in the image files, but you'll also see info hidden in audio files too. And technically you can hide any file in any other type of file, but these are just the most common. So how they do it with like image files, and actually this works for any other file, is called least significant bits. So what it's doing is it's taking your message, converting it to like binary, and then embedding the message in the least however many significant bits of the image or whatever file you're using. So the more bits you use, the more obvious it is that you're hiding a message, because it'll like change the values of the pixels more and more as you use more and more bits. So usually images are encoded with, so usually people use just the one lowest significant bit. So the way that images are represented, they're typically encoded with like 1 byte per color channel per pixel. So like a pixel is like, has 3 color channels, RGB, sometimes it'll have alpha for like the transparency, but just for this example, don't worry about that. And so what you'll do is you would take whatever information you want to hide, convert it into binary, and then go through each of those bytes of each of the color channels of each of the pixels and change the last bit in each of those bytes to whatever bit of your message. So you basically just go through your message and put each of the bits from your message into the last bit of each of the bytes. Hopefully that isn't too confusing, but this will kind of help illustrate it. So you can see here that these are like the red channels, the green channels, and the blue channels. You can see that like each row is like a different value for the colors, and it's just the last bit that has been changed. But if you look on the left, these are like the actual colors that each of these values represent, and you know, to the naked eye, you can't tell that those are any different. So this shows you just like how undetectable, or not undetectable, but how hard it is to detect that there's like some steganographic data hidden in your image. So like, here we go. So this image on the left is like untouched image, nothing hidden in it. And then this image on the right, I think it has like the works of Shakespeare encoded in it. But again, to the naked eye, you can't tell that anything is different. And unless you were specifically looking for this data, you wouldn't find it. So how do you solve this? There are a lot of automated tools that already do like least significant bits, because you know, it's just going through the bytes and then going through each color channel and then taking out the last bit. Sometimes, I mean, you can write your own program to do this if you want, and then sometimes like I have written problems in the past where it doesn't work like normal least significant bits. Like one that I did was it would alternate for each byte, for each 3 bytes, it would, or not for each 3 bytes, for each 3 pixels, it would alternate which channel it hid the bit in. So it would only change 1 channel per pixel. So like the first channel, or for the first pixel, it would change 1 bit in the red channel. For the next pixel, it would only change 1 bit in the green channel, and so on and so forth. So for that, you would like have to write your own tool. But there's lots of examples online that you can use and tweak. But for like typical least significant bits steganography, we have StegSolve, StegHide, ZSteg, and then there's just like an online decoder. I think is it Steghide, that it basically goes and isolates each of the color channels of your image, and you can like just flip through each of the color channels to see if anything looks off and stuff like that. ZSteg, I think, tries to like brute force looking for steganographically encoded data. And then I think Stegsolven, the online decoder, this is just one that I linked. There are dozens, but those just rely on like quote unquote normal least significant bits. Another type of steganography, which is not as common, but I think is way more fun, is audio steganography. So you could like take an audio, or yeah, so basically what you do is you're hiding text or images in an audio file that can only be seen by looking at the spectrogram. And what a spectrogram is it's a visual representation of the spectrum of frequencies in like that audio file. So typically when you open like a audio editing software or whatever, you're not looking at the spectrogram, right? So there are special tools, or not even special tools, because Audacity is like a general purpose tool, but there are special tools, I guess, within these programs that can help you view the spectrogram, and then which would be able to help you view the actual flag. So Sonic Visualizer is one that I really like. I think it's available. Yeah, both work on basically every operating system that is important. I don't know about Chrome OS. Yeah, and then Audacity is one that like a lot of people already have installed just for, you know, editing, simple audio editing. But basically what you do, this is a screenshot from Sonic Visualizer. So when you open it, normally you have like the waveform version of the audio file, and like maybe you can tell that something's up with it, but like you won't actually see the flag here or whatever information is being hidden. And so this is, again, specifically for Sonic Visualizer, but you would click on Pane and then add spectrogram. And then when you open it, you can see like the flag is very obvious that it has encoded it. The one thing I will mention about this is that if you listen to the audio file, it will, like, it's going to sound garbled. It's not going to sound normal. If it's like a long audio file that they give you, you know, maybe open it. Maybe they only like encoded it in like the last 2 or 3 seconds of the audio file. So like open it in here and just kind of scroll through it on the spectrogram just to see if you see anything. But yeah, honestly, if you get an audio file as a problem, odds are it's probably steganography. It could be like, in the past I've done like Morse code as audio. There are like online tools for that. But you know, if you get an audio file, try it with audio steganography to see if you get anything. And with that, I have a like mini CTF up right now. It's running on ctf.ieees.io. You can go there, and it's just, I think, 6 forensics problems that are, you know, pretty basic to like easy medium. And they're all things that I like just talked about. So yeah, you can go work on that. Let me stop the recording.